So this would be the energy stored, this would be the voltage applied, the sinusoidal voltage applied. So now, if we take the amplitude of the stored energy, and we take the amplitude of this term over, we take the amplitude of the stored energy by finding the amplitude of the voltage on this side. This is what we sort of come out with. The absolute, so the energy is going to have some magnitude, and it's going to have some angle, and we can already predict this angle is going to be it's going to be delta, which is the loss, but we don't know that yet technically, so we have to figure it out. So in order to find this term, we can find the magnitude and phase of this portion over here, because we can also represent this as a magnitude and phase, as I just showed you. So this portion over here should also be able to be represented as a magnitude and phase. So how do we do that now? So we had again 1/2 CV squared, and then we had 1 minus I tangent delta, and this equals U. So if we take the magnitude of this term, we're going to get 1/2 CV squared. Now we're going to do the magnitude first. So square root of 1 plus tangent delta squared. And because you're squaring this term, you're squaring the magnitude, you're getting an angle. This I is not going to be, it's not a real I. You're not actually squaring I. You're actually plotting in the real and complex plane. And once you plot in that real complex plane, and you get the magnitude here, and you get the phase, then you can actually know what's happening according to a sinusoidal input. So here we go. So we have 1 plus tangent delta squared. This is the magnitude, but this is not the interesting part, which I'm going to mention. The interesting part is going to be the phase. And the phase now is going to be equal tangent -1. If you remember your geometry, and you remember a triangle, and you remember how do you measure a angle in a triangle. Maybe you know, maybe you don't. So that would be U. This is UI minus, and this is UR. Because this is the real plane, this is the imaginary plane. Therefore, if we call this parameter A, and we call this then we can rewrite this equation right here like this. So we could write it as A minus IA tan delta, right? Because we call this portion right here A, and we just divide it over. We call it A minus A tan delta. This is the real part, this is the imaginary part. So the imaginary part will go on top because it's opposing the angle. The A's cancel, and basically what you're left with is delta equals tangent delta. And we already know that tangent delta equals delta because of the low amplitude. If delta is much less than 1, then tan delta equals delta, or basically tan x equals x. Tangent equals x. So there's a slight more portion for it. So I just explained to you that the energy stored in a capacitor or a piezoelectric material at a low frequency, low applied voltage frequency, much less than the resonance frequency, that the time lag from the voltage, and we define actually the voltage as sinusoidal, like here. So the voltage is equal to this magnitude, basically. So if we pull up another slide, let's go back to the beginning. Here, so we define voltage Or we could say that voltage, the magnitude of voltage, equals this voltage, the amplitude, right? And the phase of the voltage, assuming that voltage has a magnitude and has some phase, the phase is equal to 0 because we're applying it. It's sort of like a reference. Therefore, according to that reference, the tangent delta, which is the stored energy, is will then be proportional to the losses, or rather, it'll be proportional. This tangent delta will be again proportional to loss energy divided by the stored energy, which is the energy being lost due to dielectric loss divided by the energy stored in the capacitor. So the next portion you're probably wondering is, how does all this relate to current, and why does current somehow change its phase or something? So, as you may know, current in a capacitor, so if we're just looking at the basic equation, Q equals CV. If you want to argue with me here, okay, God help you. Okay, so but basically Q equals CV. I hope so. So, and V is going to be defined as VO sinusoidal. We like sines. Okay, so let's change the nice color here. So therefore Q, and this is also time varying. These are both time varying things, as you see here. This is also time varying. This is the capacitance. We're not talking about imaginary right now. But anyways, if you take the derivative, dq over dt, that's going to equal the current, which we'll call capital I, which is going to equal C, and the derivative of voltage over time, which would then equal omega, okay, VO, and cosine. So the current is by definition it's a definition in a cosine shape, because the magnitude of I equals C omega VO, and this is a way to measure capacitance using measuring the frequency, measuring the voltage applied in the current. You can calculate capacitance, but the angle here, I is VO cosine. So it goes in the cosine shape. So basically, it's 90 degrees phase lag behind voltage is current, and in phase theoretically, charge is in phase with voltage. But however, we know there are losses occurring in the material. We know there are losses occurring in the material, so maybe it'll be something different. So I already proved to you that the stored energy in a dielectric material has a phase lag of delta, which is the permittivity divided by the imaginary permittivity divided by the real permittivity. You don't really think about it like that. We usually just measure this tan delta guy. But how do we measure this phase lag from current, and why is current valid? How can we calculate charge and energy from current, and current somehow relates to tan delta as well? Okay. For that question, let's take a look at our friendly, easy to imagine friend. He's called the spring. And see, the spring also has a similar effect. If the spring is an imaginary spring constant, K star, or K is a nice spring constant, we have an imaginary term. So we have force applied equals Kx. This is the term for the spring, and we're pulling out force over here. So the force applied, the energy stored is also going to have a phase lag. So the energy stored here is going to have a magnitude, and it's going to have a phase lag, and we can assume that the force has no phase lag because it's the definition. It's sort of the standard reference point, which is causing all the things to happen in the system. So one important thing to understand is that the definition of energy stored in the spring is 1/2 kx squared, and x is this displacement in this case. This is the real energy stored. So the real energy stored in a spring is